Okay, so good afternoon to everybody. Thanks for being here this afternoon. So it's a pleasure for us to have here Stefano Bosco. Just a brief introduction. Stefano, as he told me, has a background in electronics engineering. So he got his bachelor degree at the Politecnico di Milano. And then after his master degree in nanotechnology, he moved for his PhD in Aachen, where he worked on under the supervision of David DiVincenzo on quantum Hall plasmonics and on superconducting circuits. And since 2019, he's in the group of Daniel Loss at the University of Basel, working essentially on silicon and germanium spin qubits. So he has co-authored a number of papers on the mainly the tunability of the spin-orbit coupling in these systems. And as we know, the spin-orbit coupling is what allows the all-electric manipulation of the spin qubits, and also on the tunability of the coupling of this spin qubits to the magnetic and electric environment, which are the main sources of decoherence. So, of course, this is also another crucial aspect. So we're very curious to know about your recent results, Stefano, and please go ahead.
Okay, thank you very much. As I said, my name is Stefano Bosco, and I'm currently a postdoc in Daniel's Loss group in Basel. And today I will be talking about some recent work I've been involved with on whole spin qubits in silicon and germanium quantum dots, particularly involved in how to make ultrafast gates and noise resilient qubits. Now, this work has been a collaboration with other people. So I have to thank Bence for the silicon part, and Christoph Adelsberger and Monica Benito for the germanium part. And also I have to thank the founding agency, the NCCR, via the spin grant. Now, as you mentioned, I was raised as an electronic engineer, so I always like to start my talk with a picture of a field effect transistor that, as it turns out, is a basic ingredient for a classical computer. And I'm pretty sure I don't have to explain how those devices work, especially to this audience. But let me just point out the importance of having an electric field that can tune on and off the conduction channel in those devices. Now, I would like also to stress that so there are different types of field effect transistor. The first generation were planar field effect transistor, but in more recent years, people have been interested in having three-dimensional fields that were the channel extend in the third dimension, because from a classical computer point of view, this channel provides a better electrostatic control. Now, as it turns out, those type of devices are also basic ingredients for semiconductor-based quantum computing, especially when they are tuned to a regime where there is a single excitation in the field effect transistor. So what I will be focusing on today are spin qubits that are defined in quantum dots. Now, why spin qubits? So as you might know, spin qubits have a bunch of very interesting properties. For one, they have high coherence, and they can operate at high temperature. And for high temperature, I actually mean about 4 Kelvin. And importantly, they can be made very compact, and they are compatible with CMOS technology. And those properties are very nice properties if you want to scale up quantum computer and making very large processors. Now, there are several different flavors of spin qubits. The one I will be focusing on today are spin 1/2 particles confined in quantum dots that incidentally were proposed by my current boss and my old boss when I was in Germany. So I had to work on this topic. And in those systems, there is a very important element, which is the spin-orbit interaction that enables local electric gates. Now, there are several platforms where one can implement those quantum dots. The one I will be talking about today are whole quantum dots in germanium and silicon structures. Now, regarding the spin-orbit coupling, holes have some advantage compared to electron, because in those systems, in whole system, the spin-orbit coupling is very large and it's easily tunable. In particular, in recent experiments, it has been demonstrated that the spin-orbit coupling can be tuned to be 10 to 100 times larger than in electrons. And this is very convenient because it enables fast gate at low power. for example, in this experiment, they reached alpha gigahertz of Rabi frequency. And also it's interesting because you can use the spin-orbit coupling to strongly couple the spin to resonator, which is another idea to scale up quantum computer. On top of that, holes have no valid degree of freedom, so you don't have to worry about extra states that could degrade the performance of the device, as in electron system. And also they can be tuned to a regime where they have small hyperfine noise. Now, small hyperfine noise you can also reach by isotopically purify the germanium and silicon material, but you can also reach by tuning the system to be roughly decoupled to a regime where the spin in the quantum dot is roughly decoupled from the spin in the nuclear defect spin. So one message that I would like to pass with this talk is that the dot design is crucial in whole system, and in particular, you can optimize the quantum gates by getting faster gates at low power, and you can also find design where the noise is minimized. Now, just to give a brief outline of the remainder part of the talk, I will first briefly remind the audience of the theoretical tool that is used to describe whole system, that is the Latinger-Cohen-Hamiltonian. And by using this tool, one can find some difference between the germanium and silicon quantum dots. Then I will talk about driving qubits, and in particular, we'll compare planar, heterostructure, and nanowires, or FinFETs. And I will introduce the idea of squeezed qubit. After talking about driving qubits, I will focus on idle qubits, and I will mention some ideas of how to find decoherence in FinFET qubits, in particular decoherence that is caused by charge noise, and I will introduce the concept of a spin-orbit switch, and also decoherence that can be caused by hyperfine noise. Okay, to start, let me briefly remind how to describe the valence band in semiconductor with diamond symmetry. So the theoretical tool that is used to describe the system is the Latinger-Cohen-Hamiltonian. Then in its simplest form, looks like this, and basically captures the mixture of heavy holes carrying spin 3/2 and light holes that carry spin 1/2 of the valence band. Now, this Hamiltonian is parameterized by three material-dependent dimensionless quantities that are this gamma 1, gamma 2, and gamma 3 that are called Latinger parameter. And by comparing this Latinger parameter in different materials, one can find some qualitative difference between the materials. So, for example, silicon is a so-called anisotropic semiconductor because the difference between this gamma 3 and gamma 2 parameter is rather large compared to the gamma 1. What this means can be understood by considering what the germanium is, because germanium is a roughly isotropic semiconductor where those difference is much smaller compared to gamma 1. And when the semiconductor is roughly isotropic, one can describe the first order by a simple approximation where the difference between those two parameters is neglected. And the Latinger-Cohen-Hamiltonian reduces to a rotational invariant Hamiltonian that takes on this very simple form. Now, let me point out a few differences between silicon and germanium. So silicon, of course, it's very convenient from a technological point of view. However, germanium also has emerged in recent years as a very nice playground material to define spin qubit, because this gamma S parameter here is larger than in silicon. And this means that you can have larger spin-orbit interaction in germanium compared to silicon. And on top of that, germanium also presents a small mass, as one can estimate by considering this gamma 1 parameter, which means that when you make a germanium quantum dot, you can reach the single hole regime with a larger dot. So it's technologically a little bit more easier to make single hole germanium dots compared to silicon. Now, there are several platforms to make germanium and silicon quantum dots. So the ones that I will be talking about today are basically those two classes of system. One is the planar germanium and silicon heterostructure, and the other one are the class where there are nanowires or hot wires or silicon FinFETs. I will be a little bit more precise on what the difference are later on. But at this point, let me just maybe mention that a reasonably fair statement at the moment is that planar germanium silicon heterostructure are a little bit more advanced. So, for example, in Delft, the group of Menno Velders has recently proved a fully functioning 4-qubit processor, and they are now trying to use this processor to make quantum error correcting protocols. And on top of that, there was a talk recently by Menno Velders where he showed a picture of a 16-qubit processor. So possibly it's on its way. So some new data on this processor are on the way, and this provides a very nice feeling for the future in terms of scaling up the quantum computer with spin qubits. Now, in contrast, at the moment, I want to stress that at the moment, the germanium and silicon wire and FinFETs are a little bit behind. In fact, they are still working on the 1-2 qubit type of operation and on the singlet triplet encoding of the spin qubits. And as far as I know, arrays of coupled wires where you basically couple qubits belonging to different wires have yet to be demonstrated. However, there is a reason why these wire systems are very interesting, and the reason comes from the nature of the spin-orbit interaction. In fact, as it turns out, in those systems, the spin-orbit interaction are of direct Rashba type, which means that the spin-orbit is linear in momentum compared to the cubic in momentum spin-orbit that emerges in planar heterostructure. And because of this linear versus cubic trend, the wires typically exhibit have a larger spin-orbit coupling that enables faster gate and more power efficient operation. Now, the first question that I would like to address in this talk is, can we actually recover this larger linear spin-orbit coupling that is typical of nanowires in planar structure? And this is the idea behind the squeezed Hall qubits, which was examined in this work. Now, let me be a little bit more precise about where does this cubic against linear dependence come from. And to understand this difference, it's very useful to take a look at the Latinger-Kohn Hamiltonian. First, in the isotropic approximation, and if you just write it down in matrix form, it takes on this simple form written out here. Now, as a theorist, what you do when you try to examine the difference between planar and nanowire or FinFET structure is you consider the direction of the direction where the confinement potential is stronger, and you construct a low energy theory that works in the direction of weak confinement. Now, for planar structure, the strong confinement direction is the Z direction, and the weak confinement direction is the planar direction. And to construct the low energy theory, what one does is just you take the momentum in plane to go to 0. And when you do that, you realize that the only term that matter are those purple elements here, which mean from which it follows that the ground state in this system is purely heavy Hall. So the ground state, the low energy states are purely heavy Halls. And when you try to compute the spin-orbit coupling between a heavy Hall spin up and a heavy Hall spin down, then you need to go at least to third order in momentum to get a coupling. So this is examined in detail in this work by the Sydney group, and it turns out that when you include the isotropic Latinger-Kohn Hamiltonian, you get this type of coupling. Now, in contrast, when you consider a nanowire, you have two directions of strong confinement and one direction of weak confinement. And by constructing the low energy theory in exactly the same way as before, what you observe is that what the terms that are relevant are those green terms here, which means that the ground state of the system is a mixture between heavy hole and light hole state. And this basically means that when you try to couple the heavy hole and light hole state, and you apply, you also need some electric fields here, what you get is a spin-orbit interaction, which is linear in momentum. It takes on this form. Now, this is not the full story. In fact, if it was, you would not really have EDSR in those type of system, because there is another term that emerges because of the Latinger-Kohn anisotropy. And this term is particularly relevant in planar heterostructure. So basically, you have a qualitative different term that depends on gamma 3 minus gamma 2, and couples P plus and P minus. This term, again, is the term that is actually responsible for EDSR. And because germanium is roughly isotropic, it's actually rather small. Now, if you include Latinger-Kohn anisotropies in this system, in nanowires, you don't really get, you only get a correction of this velocity. So that's why I'm not including it here. Now, to see how this translates into having electric dipole spin resonance or into driving qubits, one basically extends the low energy theory that I've been talking about so far by including the harmonic potential that comes from the gates, and is required to define the dots, and also includes the electromagnetic field. So there is some electric field that is time dependent, that is required to drive the qubit, and there is some magnetic field that is required to Zeeman split the spin up and down states. Now, so by using those effective theory from planar and nanowire structure, then one can further reduce the problem to the low energy sector and consider only only find a driven qubit Hamiltonian that in planar structure takes on this form, while in nanowires takes on this form. Now, for driving the qubits, I want to stress that the terms that is relevant is this term here, the coupled spin up and spin down state, that depends on the spin orbit coupling, in particular on the spin orbit parameter alpha 1 and alpha 2, and also depends on the time derivative of the driven electric field. In nanowire, it depends on a length scale LSO, which on this quantity LSO that is the unit of length, and it's typically called the spin orbit length because it kind of characterizes the strength of the spin orbit along the wire. Now, the detail of this equation might seem a bit sketchy, but because I didn't really show any of the derivation. However, the message that I would like to point out is that some sort of anisotropy is always required to drive the qubit in whole spin qubits. Now, from this equation, you can clearly see that the anisotropy can come from the confinement potential through this parameter delta L, which is basically telling you how much the dot is elliptical compared to circular. But it can also come from the Latinger-Kohn anisotropy through this term here. Now, if one takes a look at the current experiment, so this is the paper about the 4-qubit processor in Delft, one can see that roughly the potential seems to be more or less isotropic, and the dot is roughly circular. So in those systems, it turns out that the term that drives the qubit is the Latinger-Kohn anisotropy. Now, in nanowires, you automatically have some anisotropy that comes from the potential, and therefore the Latinger-Kohn anisotropy only renormalize the Rabi frequency. Another feature that I would like to stress, because it's very important, is that the Rabi frequency, so the frequency at which you can make a X gate, scales as the length so the size of the dot to the power 2 in a planar heterostructure, while it scales as the length to the power 4 in nanowires. So if you compare the length of the dot to the orbital splitting, this means that the product between the Rabi frequency and the orbital splitting in planar heterostructure is constant, while in this case it's not constant, and you can play around a little bit more with the length. So I will be more precise about this in a slide or two. So what this different scaling means is that basically, if you make the dot larger, it's more convenient to have a spin orbit coupling that is linear in momentum. But you can still get you can still see from here that you can also in planar structure, you can play around with the anisotropy of the potential. And this is exactly the idea behind having a squeezed quantum dot in planar heterostructure. So the idea of having squeezed quantum dot compared to circular one was analyzed in this work, and in particular in this work we focused on germanium heterostructures. However, I want to stress that the same idea can very well apply to silicon. And making the dot more elliptical is actually a small change to currently produced geometry that can have a high reward. So the system that we analyzed in this work was just an elliptical dot defined in this silicon germanium heterostructure. And what we did was just basically check what happens when you play around with the aspect ratio of the dot. So as you can see from here, when you elongate the dot in the direction of the applied AC field, you can get a very large enhancement of the Rabi frequency. Now, to be more precise and give some number, what this enhancement means for typical frequencies of, typically the driving frequency is about is in the gigahertz range, and in planar structure there is this 3 gigahertz that seem to appear very often. And you compare how much power, and you apply the amount of power that they do apply in current experiments. What you seem to this high spin orbit coupling results into is Rabi frequency that are well above gigahertz range. So in particular, if by using 1%, so when the AC amplitude is 1% of the DC amplitude, you get Rabi frequency in of 3 gigahertz. Now, so this can also have another way of formulating. So there is another way of formulating this result, which kind of taking into account that even if you get like very, very fast gates, maybe your electronics cannot really keep up. And also you, at this frequency, you need to worry about a non-rotating wave correction and strong coupling correction. So maybe in real experiment, you still want to stick to the 100 megahertz Rabi frequency that it's still pretty fast. And when you try to drive the qubit to 100 megahertz in the 100 megahertz regime, you can observe that because of the large spin orbit coupling, then you can apply much less power. And in particular, with 10 times less power, you can get this very large Rabi frequency. So this basically says that you can get by squeezing the dot, you can get fast Rabi oscillation or minimize a lot the power consumption of the system. Now, I have to make a short disclaimer here, because at this point so in this simulation we used the spherical approximation for the Latinger-Cohen Hamiltonian, which basically predicts no Rabi frequency when the dot is circular, because as I mentioned before, there is no anisotropy in the system. Now, to be more precise and to compare to current experiments, one needs to include these anisotropies and compare the result with realistic parameter with these anisotropies. And what we do find is that indeed, when anisotropies are accounted for, in circular dot, you still get some finite Rabi frequency. However, there is still a lot of advantage a lot of quantitative advantage by using squeezed dot. Now, this advantage can be appreciated also in terms of a trade-off for the optimal size of the dot. because, as I mentioned before, the orbital splitting scales as 1 over the size of the dot squared, and the Rabi frequency in isotropic in circular dots scales as well as the size of the dot to the power 2, while in nanowires it scales as or in squeeze dot it scales as the size of the dot to the power 4. Now this scaling is very convenient, and it turns out that this is actually the one that makes you the more advantage on the squeeze qubit. So in germanium, you get an advantage because of the scaling, and you have also to consider that Luttinger-Cohen anisotropy are a bit weaker. And all things considered, this results in a Rabi frequency that is 100 times larger by squeezing the dot. So this is a very convenient idea of how to minimize the power and how to increase the speed. Also, let me point out that at this point, I was just describing an ideal situation. When you study this system, typically you also have to include the strain. In particular, in this system, strain is caused by the mismatch of lattice constant between the silicon and germanium. And strain typically tends to decrease the Rabi frequency. However, even if you do account for strain, you get still more than 1 order of magnitude advantage by using a squeeze dot compared to a cylindrical dot. And again, I want to stress that this concept could very well work in silicon, even though in this work this work was restricted to germanium quantum dots. Okay, so I've been talking about how to drive qubits, but let's take a step back and see what happens when you want to store the quantum information in the qubit. So what happens in idle qubits is that you have many sources of decoherence, and in spin qubits, the main source of decoherence is dephasing. Now, dephasing can be understood in a very simple way by this simple Hamiltonian, where you have a splitting of the spin up and spin down state, and you have some randomly distributed noise. You have some randomly distributed variable that couples in the same direction as the gap. Now, a very simple description of this type of system comes by considering Gaussian noise. And so what it means basically is that you take a dimensionless variable, which comes from the integration from a certain initial time to the wanted time of this parameter, and then you study the coherence of the qubit. What it means is that you basically consider how fast the qubit decays from a pure state into a completely mixed state. Now, for a Gaussian noise, this is a very simple formula, and the decay is exponential with some the exponent that depends on the standard deviation of this quantity. Now, the standard deviation depends on the type of experiment, and in particular, in the simplest experiment, that is pre-induction decay, which means basically you prepare the state and you wait for a certain time. There is a very simple relation between the standard deviation and the spectral function of the noise. Now, from a physical point of view, there are many sources of the coherence and of the phasing. In particular, the one that seem to be more relevant for spin qubits are charge noise and hyperfine noise. So to understand how charge noise couples to qubit, let me maybe start from a nanowire and consider the same effective Hamiltonian that I showed before, where you have confinement, an harmonic confinement potential, spin-orbit interaction, and Zeeman splitting. Now, when you reduce to a quantum dot, a qubit Hamiltonian, then what it turns out is that because of the spin-orbit coupling, the G factor gets corrected by by a Gaussian factor that depends on the ratio between the size of the dot and the spin-orbit length. Now, to understand how dephasing can come about, one considers a structure where you have a gate potential that defines the dot, but this gate potential can have some random fluctuation on top of a fixed point. And by linearizing the potential, by linearizing the system with respect to this random fluctuation, one finds this Hamiltonian, which is exactly the same as what I showed here. Now, this Hamiltonian is parameterized by a quantity with the unit of charge, this Q, that depends on the Zeeman splitting, and then depends on the relative variation of the G factor, of the size of the dot, and of the spin orbit length. Now, by considering 1 over f a noise with this spectral density, then it's rather easy to see that the decoherence is, by using this theory, that the decoherence scales as a Gaussian, where up to logarithmic correction that cuts off the small frequency divergence here, so the time scale can be given very simply by this formula here. And what I want to point out is that when you have large spin-orbit coupling, this term is rather large, and therefore you can get a very large susceptibility of the qubit to charge noise. This problem is very much relevant for elongated qubits, squeeze qubit or wire qubits, where the spin-orbit coupling is very large. But luckily, in this system, the amplitude of the spin-orbit interaction is highly tunable, and they can be tuned by the dot design. Also, this tunability is useful when you want to selectively couple a specific qubit to an external resonator. So this is not just about charge noise, but it's also relevant for coupling different qubits that are far away from each other. Now, I mentioned that the dot design matters a lot for tuning the spin-orbit interaction. In particular, one of the features that matters the most is the symmetry of the cross section. So, if one considers fin that has this particular inversion symmetry, it turns out that the spin-orbit interaction have this form, and they are linear in the applied electric field, in the applied DC electric field. Now, what this means is that the only way to get zero spin-orbit coupling is by tuning the dot to a regime where the electric field is strictly zero. And this is a problem in electrostatically defined dots because this electric field is rarely equal to zero. And this converts into a residual spin-orbit interaction and residual charge noise. Now, a different system, a different case emerges when one considers triangular FinFETs, where the cross-section is not inversion symmetric. In this case, in fact, it turns out that there is not just this linear and electric field term, but there is also an intrinsic spin-orbit coupling that can have the same sign or the opposite sign with respect to this term. And what this means in terms of switching off the spin-orbit coupling is that you can have points at finite electric field where the spin-orbit vanishes. And at these points, you actually can reduce a lot the charge noise. So now in this work, we analyzed this effect in great detail, considering these three growth directions. And in particular, what we found is that this spin-orbit switch emerges because, of course, because of the inversion asymmetry of the fin, but also because of the Latinger cone anisotropy. And because this is an effect that depends on the Latinger-Cohen anisotropy, this is an effect that is enhanced in silicon compared to germanium. And also, again, because this is an effect that depends on the anisotropy, it also has a very different effect. So the cancellation can only occur for certain growth directions. So it turns out that the more interesting cases are when at least from a theoretical perspective, are when the fin is grown along the 001 direction. And in those cases, for equilateral triangles, one can find an effective, one can find a simple formula that captures this this intrinsic spin-orbit coupling. And this formula is what I write here. And what I want to stress is that so there are two terms, one of which is an anisotropic term that depends on the growth direction, in particular on the angle of rotation between the crystallographic axis and the confinement axis, as one can see from here and here. And this term also captures completely the intrinsic spin-orbit interaction. So this term here that is independent of the electric field. There is also another term in this equation, which is coming from the isotropic Latinger-Cohen Hamiltonian, and for that it's independent of the growth direction, and also contains the Dirac-Rashba spin-orbit coupling linear in the electric field. Also in this equation, I also include some higher order correction that scale quadratically in the electric field, because those are also required to understand the switching off of the spin-orbit coupling. Now, before analyzing this equation a little bit further, let me point out that this is not just some crazy theory prediction that could never be experimentally seen. In fact, this has actually been seen before in this work by the Katsaros group on germanium hot wires, so triangular hot wires. And in this work, they measured an intrinsic spin-orbit coupling when there is no electric field that is pretty much in agreement to the one that we estimated for germanium in this work. So this kind of it's a nice consistency check that what we do actually can capture reality, and it's not just some crazy theory. So with this in mind, we can also examine with a little bit more confidence the effect of electric field in silicon FinFETs, and this is shown here, where I basically show the comparison between the spin-orbit coupling that emerges in those three growth directions. Now, for positive electric field, which is the typically experimental relevant situation, we see that the convenient orientation of the fin is along this Dirac-Rashba axis, and where one can find a point where the spin orbit is switched off. Now, this can be understood from this equation, because if the fin is growing in crystallographic axis, then this term and this term have the same sign, and they cannot cancel each other. While in the Dirac-Rashba direction, this term takes a minus sign and has the opposite sign on this term, and therefore you can get a cancellation and a spin orbit switch. So we focus on those type of devices, those Dirac-Rashba silicon FinFET devices, and we examine charge noise in the way that I showed before. So basically, by considering this quantity Q and comparing the effect of the G-factor noise, so the fluctuation of the G-factor, with the effect that it's related to the spin-orbit coupling. Now, it turns out that the spin-orbit noise is the one that is dominant in for most of the gate potential. And what the G-factor noise does is just shift a little bit the position where the charge noise is removed from the spin orbit switch to a slightly higher gate potential. So basically, the take-home message of this analysis is that if one can make this direct crush bus silicon FinFETs, and one can isolate the qubit inside, then one can find points where the charge noise is suppressed. And those points are very close to the point where the spin orbit coupling is removed. Now, let me also, as I promised, I will also briefly discuss the effect of hyperfine noise. And the hyperfine noise is known to be a very tricky business for spin qubits. And it basically emerges from the fact that you have a spin with a large wave function that is confined in a dot. And in this dot, you also have a lot of nuclear spin defects that have some spin and can couple to the spin of the particle, the spin of the qubit. And this coupling leads to dephasing. Now, there is a lot of microscopic theory that defines this dephasing. I don't want to enter too much into details, so let me just state that the coupling of whole spins to randomly distributed nuclear spins, I of k at position rk, can be described in this way, where this parameter delta is depends on some bulk coupling, hyperfine bulk coupling between the spin of the qubit, and the nuclear spin defect, but also it depends on this matrix gamma that it's basically some matrix that strongly depends on the quantum dot design, and in particular it depends on the heavy or light hole mixing and on the spin orbit interactions. Now, if one doesn't consider isotopically purified material, typically in silicon qubits you get about 100 defects that have a slow dynamics, and therefore this quantity is varying very slow in the scale of the time of the experiment. And what this means is that by applying this theory to this type of quasi-static noise, you get a Gaussian decay with a time scale that depends on this bulk hyperfine coupling, A of k, and also depends on the size of the dot. So this n basically quantifies how many atoms are in the dot, and on the percentage of nuclear spin defects nu. So just to be a little bit more quantitative, this quantity here in natural silicon is about 0.4 microseconds for a dot that has 10 to the 4 atoms inside. This is not the full story. In fact, this time scale also depends on a dimensionless parameter delta that can be very easily tuned by external fields and also by the direction of the magnetic field. Now, I don't want to go too much into detail, so complete analysis can be found in this work here. But let me just point out that when one tries to examine the performance of a direct crush by silicon FinFETs, because of this tunability of this delta parameter, one can find sweet spot where the hyperfine noise is very much decreased. Now, at the sweet spot that basically come from a line in the magnetic field along the fin or perpendicular to the substrate, you can get an enhancement of the hyperfine. You can get a reduction of the hyperfine noise by a factor of 20, which you can compare to the enhancement that you would get by isotopically purifying the material. So when you isotopically purify silicon, typically you reduce the number of nuclear spin by 2 orders of magnitude, which in turn means that you get an enhancement in this time scale of about a factor 10. So this enhancement is pretty much comparable with what you get just by rotating the magnetic field in an appropriate direction. So you get comparable performance. However, I would still argue that it's interesting to look into this system because it's much cheaper to rotate the magnetic field rather than isotopically purify the whole system. So this actually can save potentially a lot of money in the manufacturing process. On top of that, this hyperfine sweet spot turns out that also coincides with the spin-orbit switch when one considers equilateral triangle. And this is very interesting because it means that potentially one can get highly coherent idle qubits that are largely unaffected by both charge and hyperfine noise. And so this is an ideal platform where to store quantum information. And if you want to drive, then you can just electrically move away from the sweet spot and then drive the qubit. So finally, let me just comment that, again, we did a consistency check with some current experiments where the fin is grown along the 110 direction instead of the 001. And what we found is a reasonable agreement between our estimate from this simple model and the value that were actually measured in this work. So again, this is a nice consistency check that sort of motivates into the idea into looking into this system, because it's not just it seems like it's not just some crazy theory result, but it can be very well seen in experiment. So with this message, let me come to the conclusion. So during this talk, I've been talking about whole spin qubits in silicon and germanium quantum dots. And I first focus on driving qubits, on the way of driving qubits, and I compare planar and nanowire. And in particular, in those two systems, one gets a cubic or linear spin-orbit interaction. And the linear spin-orbit interaction results in faster quantum gates at low power. And then I introduced the idea of squeezed Hall qubits as a small modification to planar structure to get 2 orders of magnitude enhancement in the Rabi frequency. Then I discussed some design concept to make idle qubits more resistant against noise, in particular charge noise and hyperfine noise. And those ideas were mostly converging onto the silicon FinFET, in particular silicon FinFET growing in this direct rush-bar growth direction, where one can define spin orbit switches, where charge noise can be removed, and also a sweet spot where the hyperfine noise is less relevant. And if one considers triangular silicon FinFET qubits, then one can actually have those 2 points to coincide, resulting in highly coherent quantum bits. Okay, so with this, I would like to thank you for your attention. And of course, if there are questions, please tell me.
Okay, thank you very much, Stefan, for this very nice presentation. So the paper is now open for discussion. There are questions. Yes, Michele, please go ahead. And Enrico. Okay, so Michele, please, and then. Okay, so we have many questions.
Okay, so please unmute yourself. I don't really see if there is some chat or anything.
Michele, we don't hear anything. I don't know if you're. Okay, so. Shall we start? Shall we go on with Enrico? Michele, there seems to be some problem. We cannot hear you. Enrico, can you please ask your question?
So this is Enrico Cancelari from Modena. So thank you very much for your nice presentation. I got a curiosity. So I imagine that when you reduce the channel below, let's say 10 nanometer, you can have some leakage current due to direct tunneling. So do you think that this is an issue in your case? And if so, how you think that it's possible to introduce this also in the modeling? Okay, so
okay, let me point out. So okay, I was talking about 2 different systems. So in this case, I don't think there's much of an issue, and the reason is that the channel is actually not really 10 nanometers, but it's much larger. So this is the planar a cut of the cross section, and you see that this is pretty large. So this is about 50 nanometers from the metal to the germanium quantum well, where the dot is defined. Now in silicon and germanium, in FinFET structure, this is different. So you might have tunneling of electron inside of the qubit. I think you still have some Coulomb blockade that will prevent this, and you have some time scale associated, for which ultimately you need to be aware of leakage. But I mean, surely there have been studies, and there have been many experimental demonstrations that this is not too big of an issue, at least for this system, because they were able to define the quantum dot very nicely. Let me find some picture where this is shown. So there are some these Coulomb diamond experiments where you can actually see how many electrons are there, and so I'm actually diverging a little bit, but yes. So quantum tunneling can be an issue, but I think it's not the biggest issue, at least at the moment. Let me put it this way.
Okay, thank you very much.
Okay, Michele, are you now able to talk?
Can you mute them?
Okay, we still cannot hear about Michele, so
Hear it now?
Yeah, now yes.
Okay, sorry, there is some issue, as you can see, with audio. I hope you can hear me now.
Yeah.
Hello?
I can hear, yes.
So we are encountering a problem with the audio. Can you hear me now?
Yes.
Okay, so sorry about that. So we were not able to understand exactly what's going on. So thank you very much. It's Domenic actually here. As I said, we are sharing the projection in our lab. I'd like to thank Stefano for the very interesting talk. Obviously, I wasn't able to understand everything, so it would take years of work or studies. But I had a question before this talk, and I was thinking myself about the impact of 1/f noise. And actually, there was it came out this talk. Stefano touched this, and the question is, Stefano, it's where I can find out more about the reference to your work. Is the PRX quantum that you published in 2021, or some other publication where we can read more about that?
Yes, so the noise part was, so the charge noise part, so the 1/f noise part was mostly in that work. I wouldn't claim that's a comprehensive review of anything. This is a very specific work addressed to those type of FinFET structures in silicon. For general references for 1/f noise, I'm actually not sure exactly what to recommend. I mean, I know there is a little bit of it's a little bit unclear what causes the 1/f noise. Typically, people associate it to some fluctuating two-level system.
But no, of course. So I know a little bit about the flicker noise myself, and I understand that not everything is clear there. But my question was specifically about the effect of flicker, let's say 1/f noise on the spin charge noise. So on the charge noise. So you said that you targeted specifically for the FinFET, but is there any place when we can read not only about that, more about that, and not necessarily specifically for the FinFET?
Yes. So I can recommend this work by John Martinez.
Okay.
So this work is it's actually about superconducting qubits, but they do have some very nice theory where they where they discuss this model Hamiltonian, and they discuss dephasing in this Hamiltonian.
Okay.
And ultimately, what it turns out, so what the relevant features is that when you assume that this variable is Gaussian distributed, then you can relate the decoherence due to dephasing to the spectral function of the noise, and then you can get different for different experiments, you get a different prefactor here. So this is a pre-induction decay. You might have heard about something that is called dynamical decoupling. So spin echo expect where you get different scaling here, and you can sort of decrease the effect of 1/f noise because you don't care too much about what happens at zero frequency. But this is okay. I'm diverging again. So this is all very well explained in this work here.
Do you think my understanding was that you mentioned at the very beginning that it's targeting superconductive qubit, but there is something more than, so it's let's say specific for superconductive qubit, or can be also no. Let's say more general the content of this article.
Yes. So it's okay. So here the examine. So what differs in this context from superconducting spin qubits is the sources of noise. So you can have charge noise, you can have hyperfine noise. But what this article does very well is discuss this theory and the relation that brings you from this Hamiltonian to basically this relation here.
Okay. Thank you very much, Stefano. Thank you. So we know now some good reference where we can study a little bit more. Thank you.
You're welcome.
Okay, so I'm following the order in which the hands were raised. So Andrea Secchi, please.
Okay, hello. So I'm Andrea Secchi from Modena. Thank you, Stefano, for this very nice presentation. So I have a question about your work on the FinFETs. So the wire with the triangular section. So you talked about the term which you get from your effective Hamiltonian, which is linear in Z. But you also get from the Luttinger-Korn Hamiltonian a term which is proportional to PZ squared. So the kinetic energy, the effective kinetic energy term. So I would like to ask, is the term diagonal in the space of the qubit? Is it proportional to the identity, or do you have an effective mass tensor?
Okay, so no, I mean, so if you have no, so when you restrict yourself to a wire, so okay, let me maybe go to. So when you restrict yourself to a wire system, and the mass is basically proportional to an identity unless you start to add a magnetic field. When you do add a magnetic field, you can get off diagonal, you can get some spin dependent mass. Let's put it in this way. That basically will correct the G factor. So it's a term that starts at weak magnetic field is just linear in B. So you can think about it as some K dependent G factor, if you will. I don't know if that was exactly the question that you were asking, or
yes, no. Because since the term PZ squared basically distinguishes between heavy and light holes, and it gives different effective masses to the heavy and light holes. I was expecting it to also to translate in a tensorial structure in the space of the qubit, in the spin space.
Yes. So at zero magnetic field it can't do because of time reversal symmetry. So if you want a time reversal Hamiltonian, you cannot have another sigma, a term that is like p squared dot sigma. This is not allowed by time reversal symmetry. However, when you do break time reversal symmetry, this term can arise, and then yes, then you can have a spin dependent mass. And but you can also see it as some correction to the G factor, if you will.
Okay, thanks.
Okay, so Francesco Rossella, please.
Yes, hi. Thank you, Stefano, for the talk. I just have a curiosity that is the following. If I take a core shell nanowire, silicon germanium core shell nanowires, and I look to the edge instead of to the face, I look to the edge. What I see is something very similar to this hearth grown by Katsaros. And I always wanted to ask to Katsaro, but I had no opportunity. So I asked to you, So from the point of view of the, I mean, not of course with these structures grown like Katsaros, you get scalability, and you can realize an array of these objects, as they did in this nice paper you were citing, this advanced material what. And this is a good point, of course. But in terms of what you gain from the material point of view, no, in terms of the spin orbit interaction and so on and so forth, is this hot structure really giving you a plus with respect to a core shell nanowire made of silicon and germanium? It's just a curiosity, because actually, really, if I look at the edge, what I see is exactly this shell of germanium surrounding a core of silicon. So from the material point of view, it should be very similar to the Katsaros height.
Yes. So okay. I think I can answer the question by showing some picture. Yes, so you can have something like this.
Well, but this is an hexagonal structure, you know, an hexagonal cross section typically with
yes,
if I remember well, no? Yeah, okay.
Well, I mean, it's roughly cylindrical, so I'm not sure if it's
cylindrical. I think it's difficult actually. You should have some kind of triangular or hexagonal shape, no?
Okay, so let me point. So okay,
you have hedges for sure. You have facets and hedges. Facets and hedges. This is for sure. So
yes. So from what I mean, I'm not an expert in how those things are grown, but what I know from what they do here and is that typically, even if it's hexagonal, you still have this inversion symmetry, which means that you have something like some spin orbit coupling that looks like this. Again, this means that at zero electric field, so if you don't have electric field, then you don't get spin orbit coupling.
Yeah, I got the point. So you have a strong anisotropy due to the fact that the hut has its
yes,
this substrate somehow. Okay.
Yes. Also, it's true that Katsaros, Georgios Katsaros grows it in not in a very convenient direction for having the switch. So, even there you have to rotate. So what I think what he uses is some axes that look more or less like this, maybe with some rotation here again. But, the point is that the direction of the wire is in the 110 direction instead of the 001. So for having the spin orbit switch, it's crucial that you get this 001 direction. And on top of that, you have this hot or triangular triangular fin structure. So yes, I mean, so there is some work to be done there. But what I can tell you from a theorist perspective is that if you have the core shell wire, typically you will not get this extra term, this extra zero field term, and this means that I mean, unless you have some inversion of symmetry breaking, and this means that you cannot get this switch at finite field.
Yeah. Okay.
Also, maybe I should stress. So this work about the triangular FinFET was actually motivated not really by Katsaros group, but was more by some effort in house by Andreas Kuhlmann, where they actually made I need to find it. Sorry, where they actually made like a silicon FinFET that is roughly equilateral and looks like this. So this work was actually more about trying to understand this guy, and it turns out that also you can understand Katsaros' work, and then there was an unhappy extra side effect of the analysis.
Okay, thank you very much.
Okay, so there's a raised hand by Alessandro Crippa. So please go ahead.
Yeah, ciao Stefano, thanks for the nice talk.
Thank you.
I'd like to ask you a question about the planar structures like the ones used by Menno Belders in Delft. What would you think? It would be more efficient to go towards the elongated dot idea to drive the EDSR through a lateral gate rather than a plunger gate? Would it help?
Yes. So to get yes, of course, to get this squeeze dot working, what you have to do is to have some electric field that is applied, that is has some component in this direction. Now, yes, to do that, typically you have gates here, and then you drive with some gate here. Or you have maybe a gate here that defines the structure, and then you have some extra gate here, and you apply the time dependence confinement, the time dependence potential to a side gate. Yes, so the short answer is yes. I think it's still beneficial because it's still 2 orders of magnitude larger. So maybe you have to think a little bit better the electrostatics of the design. But
yeah,
I mean,
so
I think
you have to avoid maybe problems of crosstalks between the qubits and stuff like that. But
yes, but you still have those problems in this structure, and as you scale up, then you inevitably will end up in this crosstalk term. But my point would be, in that case, you don't have to worry too much about other problems such as heating, because maybe you have to drive at much weaker power, and when you have many qubits, that could make a difference. So yes,
and
that would be my answer.
Just another short question. Do you know what happens if you apply a perpendicular magnetic field to these planar structures?
Yes, so nothing too weird happens for the qubit. So what you get is typically a larger G factor. So you can apply weaker magnetic field, and if you're thinking about some sort of Landau quantization, because you have a larger G factor out of plane, typically you don't get to a point where this matters too much.
I see. Okay, thanks.
Yes.
Thanks a lot.
Okay, so Laura Bellentani. We cannot hear you, Laura.
I can't hear you.
Sorry. Hi, Stefano. Thank you for your presentation. I have a question regarding the Rabi frequencies that you showed us. Please move to the slide.
Yes.
Regarding the squeezed dot.
Yes, I'm getting the
map. Yes.
This one or the one after?
This one.
Okay.
I would like to understand better which is the interplay between the confinement in the transverse and the perpendicular direction. So.
Okay. So I'm not. So for transverse direction, you mean like this direction?
Yes, that's
or
one
this?
and the one.
Yes. So okay. So basically, the interplay. So when you apply an electric field, strong electric field in the perpendicular direction, which you do require for having inversion, symmetry breaking, and spin orbit interaction, what you actually do is you basically compress the wave function into a length, which is this that I call here LE, which scales as the electric field to the power 1/3. And for germanium, it's this 8 nanometer value here. Now, what this plot shows is that you can get large Rabi frequency when you squeeze the dot. However, it also shows that you get large Rabi frequency when this transverse direction is roughly comparable to this length scale here. So the interplay would be, you go from, you need to have some sort of electrostatically defined wire, if you will.
Okay.
And when you do, then you can have a large direct rush per spin orbit coupling. Of course, so the optimal point, of course, when this length is roughly equal to this, but you can have like a large enhancement even for a weaker condition where this harmonic confinement length is weaker than. So it's longer than this electrostatic confinement length. This is actually the idea that I'm trying to convey here with those two different length scale. So this is the optimal, and this is the alpha optimal, where basically you have half of the Rabi frequency.
Okay. Thank you very much.
So I hope this answers the question.
Yes, thank you.
Okay, there's a final question by Sorin Bonigescu.
Hi, Stefano, can you hear me?
Hello. Yes, I can.
Sorry, I missed the first half of your presentation. I was in another meeting, but it looks very interesting. So I'd like to ask you a couple of questions about these structures, this one and the one with a triangular FinFET-like structure. So I think Alessandro just asked you about that, so I just want to make sure I understood correctly. So if you apply a magnetic field on this structure along the z direction and the electric field also along the z direction, you said you get higher gyromagnetic factor?
So if you apply the magnetic field in this direction,
yes,
typically you
in
get
the same direction as the electric field.
Yes, so typically you get a larger G factor, and this comes from the fact that you get you have this anisotropy of the heavy hole light hole, and so the G factor in this direction is typically given by some weaker anisotropic term, while the one that comes from the perpendicular direction you get from it's the pure heavy hole G factor up to some correction, and therefore it's typically larger. So this is not completely true, because in this case you actually squeeze the dot, so it doesn't have to be much larger, but it's typically comparable in this direction and in the perpendicular direction. So actually we did compute the G factor in this work. The G factor also depends strongly on the confinement, the size of confinement, and also on orbital effects and Landau quantization. But a rule of thumb is that when you apply it in this direction, it's typically larger. So that's what I can say.
And the thickness of the silicon germanium layer compared to W, the germanium layer, roughly, that ratio doesn't matter. So it's
yes, so so at strong electric field, then it doesn't matter that much. And by strong electric field, I mean, like, for example, when you have what matters is the ratio of this W with respect to this LE, and we estimated that when this ratio is greater than 3, then you roughly have no effect due to the back part of the germanium.
So you have an electric field of 1 volt per micron, so that would be like 10 to the 4 volts per centimeter and range. So do you consider that a large field or a small field?
Well, so that depends, I guess, on the experiment. So from talking to Menno Veldorf, he seemed to be very convinced that the electric field they get is between 1 to 10. So I think 1 to 10 volt per micrometer. So I think this is a reasonably large field, but still very experimentally feasible.
Yeah, in a MOSFET, you have about 10 to the 6 volt per centimeter for 1 volt applied on the gate. So this 10 to the 4 will take you to about 10 millivolts, which would be a good amplitude, I guess. Okay,
yes.
So with that 10 millivolts, you have some numbers there with 10 millivolt times nanometer, or 8 nanometers. So that's the spin orbit of the hole, I guess, 8 nanometers.
Yes, so maybe let me comment about this. So in silicon MOSFET, I guess you also have a much smaller distance between the gate and the position of the dot. Well, this will mean that you have a larger electric field in that case, and typically, yes, that's better. But also depends on what you want to do and what type of structure you want to consider, because the spin orbit coupling grows and then starts to decay with the electric field, and the point where it starts to decay depends on the type of qubits you're considering. So for silicon, I'm not actually sure when it starts to decay with respect when one considers this squeeze dot.
So what you're saying is that if I increase the magnitude of the electric field, that would be the small AC field. At some point, I will get a maximum of the Rabi frequency, and if I keep increasing them, then it will start to drop. Is that what you're saying?
Yes,
okay,
that's exactly what I'm saying. Yes.
The other question I have is in that FinFET structure, triangular structure. I think you have it on slide 12. So I think what you said is very valuable about trying to cancel. Yeah. So if I understood you correctly, you could actually cancel the nuclear spin impact at the same sweet spot, and that would be good when the qubit is isolated from everything else. You have it idle, like you say, and then you said that you can then, obviously, you want to turn on a strong gyromagnetic factor after that to be able to manipulate the spin. So how would you change the gate voltage in that case when you have a structure like this? Because that electrode covers everything. So how can that change the direction of the electric field?
No, so you don't need to change the direction of the electric field. You just need to change the amplitude of the electric field to move away from the sweet spot.
Oh, so that sweet spot is a function of the amplitude of the electric field that you applied on the gate, not so it'll depend on the AC field magnitude. Is that what you're saying?
No, it depends on the DC field, but
Okay.
It does not depend on the direction. So you're talking about this plot here.
Okay, so you just change the value of the voltage, and that will move you away from the sweet spot.
Yes, exactly.
And you really need that triangular structure, because a practical production FinFET today is it's a very tall fin, and it's rectangular. There is some gate at the top, but the width of the fin is maybe 1/10 of the height of the fin. And you would still have the gate surrounding on both sides. So I'm trying to understand, how is that any different from this triangular structure?
Well,
you maybe have an electric field at an angle relative to the vertical field. So again, what if, in this case, if I understand you correctly, you apply the DC magnetic field along the channel dimension, which is 110, which is how present MOSFETs have the channel direction between source and drain. Some are 100, but most of them are along the 110 direction. So you apply the magnetic field along that direction.
Yes. So
why
actually,
if you apply it vertically?
Okay. So I have to stress that for this to work, you need to grow it along the 001 direction or 100. So this pin needs to be along the 001 direction, not along the 110. So that's required to get this point. And then what this means, what this plot shows, that you can apply it in this direction or in this direction along the fin, and you still can get rid of the hyperfine noise. Also, you mentioned that all the devices are square or rectangular. I know that there are a lot of devices that are square or rectangular, but I mean there is some effort, at least here in IBM in Zurich, where they are making triangular devices. So it's not so far-fetched to think about equilateral triangular FinFETs. So let me comment this.
But sure. But IBM is out of this business. So if I look at a TSMC or Samsung FinFET, they are the ones that make production FinFETs, and they are very tall and rectangular. So in one of those, how would this behave? I understand that now you have the electric field at an angle relative to the magnetic field that is no longer 90 degrees or 0 degrees. So you really need 45 degrees or something like that. What if it's parallel or perpendicular?
So I can comment on that. First, let me point out that for the charge noise sweet spot, there is not much you can do in that case, because you don't have this inversion symmetry breaking, and therefore, in principle, you can't really get this cancellation of the spin orbit coupling for certain electric field. However, for the hyperfine noise, it turns out that you can actually, even if you have like a square cross-section or a rectangular cross-section, you can actually find a sweet spot for the hyperfine noise. Unfortunately, I don't have the plots here, but they look reasonably similar to this one. So the plots are shown in this work here. But in that case, what you need to do is apply the magnetic field. So suppose that this is a square or a triangle. What you need to do is apply the magnetic field.
A rectangle. That's what.
Yes, rectangle. I meant rectangle. Sorry. So then you need to apply the magnetic field along this direction, and you still can get a sweet spot, which is kind of the opposite that you get in a triangle, where in this direction you get the maximum of the hyperfine noise.
So I don't want to monopolize the discussion here, but if you then go to the other section, to the other structure that you show, which is more like an FDSOI structure, then what you're saying is that the one
which
we
one?
see germanium stack between two SiGe layers.
Oh, okay. Yes, this
so
one.
what you're saying, if you apply the vertical field here, you could get a sweet spot, a vertical magnetic field here. So let's assume the gate is on the top of the silicon germanium layer, where you and so this looks like an FDSOI structure to me. So if you apply the vertical magnetic field along the same direction as the electric field, then you could find a sweet spot for hyperfine interaction.
We did not examine the structure. I don't think so, and the reason why I don't think so is because this is germanium, and in germanium, you really this hyperfine sweet spot is actually something that emerges more easily in silicon. In germanium, it doesn't seem to be so easy to get to these points.
But let me ask you another question then. How is this structure different than the FinFET structure? Because you just rotate it by 90 degrees, and that's the difference between FDSOI and FinFET. It's the same structure rotated by 90 degrees.
No, it's not the same structure. So from a theoretical point of view, there is a big difference between this structure and the other one. And the difference comes from the fact that this is not etched. This is smoothly defined. So this makes a lot of this. This makes a huge difference when you try to study the properties of the quantum dot. So this is a smoothly defined quantum dot, and not really something that is etched. So it's not really just about the direction of the magnetic field and the amplitude of the magnetic field and of the electric field, but also strongly depends on the type of confinement that you add. And in this system, is roughly parabolic. So this has some consequence on the properties. So I don't know if this answers the question.
Okay, thank you. Yeah. Anyway, it's been very interesting. Very good presentation. Very nice.
Thanks.
And you're saying that it's 100 times faster rapid than the electrons. That's when because I missed that.
Yes,
part.
in theory, and but hopefully also in experiments.
Okay, so I would ask a final question, if I may. I mean, the discussion has been long, but it looks like everybody's very interested. So I'll ask a final question concerning the prospect of the, let's say, approach based on these elongated dots in this hot wire nanostructures. So could you just comment on what are the main obstacles? For example, in the, let's say, for scaling up the system and for realizing all the main tasks, including 2-qubit gates and all this. For example, I was curious about the interaction between two coupled quantum dots, which is typically discussed in terms of let's say, weak interdot coupling regime, right? So where let's say, the tunneling energy, let's call it, is small compared to the infradot excitations, which here might not be the case due to the, let's say, loose confinement along the axis direction, the non-wire direction. Could you comment on that? Is there some idea on how to work that out?
Yes. So, well, I mean, sure, there has been a lot of work on that. So I can quote some work from Ben. So from Ben's, he's been working on exactly what you're saying. So some 2-qubit gates. So I don't really see, so this guy here, I don't really see a problem in the weak tunnel coupling regime, because this is actually also true for the electron that you are in that regime. And even if you have larger tunnel coupling, typically the theory well describes the system. However, let me point out that in whole system, there are some extra effects that do not really arise in electron counterparts. And those systems are basically coming from the Latin-Gerconian anisotropy and the Latin-Gerconian Miltonian, and the Latin-Gerconian anisotropy in particular. And so, if you try to encode a single triplet qubit, then you have to also be aware that there is some zero field splitting between the singlet state and the triplet state at zero magnetic field, which is a very interesting phenomena that has been measured in Katsaro's group. And that can be actually directly related to the fact that you have Hall carriers instead of electrons. Also, because of the strong spin-orbit interaction, you might have different leakage channel when you want to do this kind of encoding. But on the other hand, it also makes the system easier to drive, because if you have like a single triplet qubit, what you want to have is some different type of G factor in one qubit with respect to the other. And this is extremely easy to do and extremely easy to tune in whole system. So potentially one can tune to a regime where you have no X components, so that decouples the spin up and the triplet, singlet and triplet state, to a regime where you actually have some strong coupling between those two states. So to kind of summarize what I just said, I don't see any particular problem in scaling up the system other than the conventional one. So how to read out this, how to read out fast enough the qubit, how to make quantum error correction, how to avoid I don't know, heating. For that, actually, one can use the squeeze qubit, for example, well, also, there's this problem of how to make circuitry small enough to fit all in the fridge. So, but those are all well-known problems that would apply to both whole spin qubits and electron spin qubits. So to summarize, yes, I don't think that whole spin qubits have many more problems than electron spin qubits when it comes to scaling up, and are actually more advantages than electron counterparts.
Okay. So if there are not further questions, I would thank Stefano very much. It was a very nice
thank
talk.
You. Thank you for inviting me.
And yeah. Okay. Thank you to everybody.
Goodbye.
Bye.
Bye. Bye. Thank you.
Bye. Thank you.
Bye. Thank you.
Bye. Okay.
Puoi scrivere grazie Stefano. Da Horus.
Federico